Hi everyone. So today I'll talk about a paper that proposed a novelty method on producing embedding for node in a graph or in a network, if you want to use that term. So first, let's talk about how it does this. So normally when they try to produce a vector embedding for vertex in a network, they would usually use the edge information between the vertices. But in this paper, the method proposed in this paper will utilize a method that would take into account both the edge information as well as the textual information of each node. And it does via leverage on neural network called Variational Autoencoder. So let's first talk about the rationale behind the Variational Autoencoder to see what it's actually doing. So first we have the generic encoder, which is just trained to reconstruct an input that has been passed through a bottleneck here in the part in the middle, and the lot is just calculated as how much of a difference between the reconstructed version versus the original version of the input. So passing through a little bit, this is just to reduce the dimension in the original input. As you can see here, suppose that with the original input you have 7 dimensions and you want to reduce it to like 1 or 2 dimensions. The further you go down, as the further you reduce the dimension, the more information will be lost, but the more compact data your data would be. But this also it could also be used for denoising in the data. So now let's talk about the content generation on the autoencoder. As you can see here, in the training process, we have trained so that the encoder will try to learn a compact representation of the original data, and the decoder will actually will be trained to decompress from the compact version of the encoded version into the original data, right? So when they talk about content generation on autoencoder, what they actually mean is that after we train both the encoder and the decoder, we will just take the decoder and then we randomly just sample some of the data from the reduced dimensional space, and then we put it to the decoder so that it would generate a new data. So let's talk about why this approach does not work for normal encoder. Okay, because when we are training normal encoder, we just define our loss function as the difference between the reconstructed version and the original version of the data. We have no regulation. What it means is that the autoencoder will be allowed to over optimize so that each point on the latent space would be highly optimized for that, so that it can reproduce back to the original version. This also means that when we are randomly sampling data from the latent space and we put it into the decoder, it would produce meaningless content, because it only optimized for certain point in that latent space so that it can produce, and only for that, only these point will produce a meaningful output, and any other point on that latent space will produce some nonsense. So in order to make the content generation possible, we need to ensure that our autoencoder have 2 attributes. First is that continuity, which means that two points that are close together in the latent space should have similar meaning. And the second is that when we are sampling point from the latent space in optimized space area, it should give meaningful content. Which means that if, for example, right, you see a circle here and a rectangle there. For example, if we randomly sample a point in the space between that two points, it should give a representation. It should give a content that is kind of similar to both of the content. In this case, it should give something more similar to this one instead. So to that end, we will introduce the variational autoencoder. So the main key difference between this and the simple autoencoder is that here in autoencoder we are taking a compact representation and then we put it to the decoder. But here this is different. The encoder will be trained to produce a distribution, right? And from the distribution, we will sample a representation, and the representation will be given to the decoder. So this is just to ensure that points that are close to a point in the original input, which is within a distribution of that has the mean of the origin of the point that is present in the data, will give meaning. We give content that is similar to that, as close to that point as possible. And we can see that right here the loss function is different too. Right here you can see that this term is similar, right? It's just the difference, the square difference of the reconstructed version versus the original version. But this here is different. This is the regulation term here. So basically this means that this is the Kublai-Leber diversion, and what it is trying to do is that if the difference between the distribution is the more different these two distribution are, the bigger this term is. This is so that it is forcing every distribution produced by the encoder to be as close to the standard Gaussian distribution as possible. To ensure this property, which is that every distribution produced by the decoder should be as close to each other as possible, so that we do not have the empty space that will produce meaningless content. So if we do that, we also have to tackle a problem, which is that how we can backpropagate the loss from the decoder. Because right now the input to the decoder would be a point sample from the distribution. To do that, they would do a reparametrization trick, which is that they will rewrite the point sample from the distribution as a linear combination of the mean and the variance. And as you can see here, if we do that, we can backpropagate the loss calculated as normal in a normal network. So this is the final overview of how variational autoencoder work. It will produce a mean and a variant. It will produce a mean and a variant, and from these two we will sample a point that we will feed to the decoder, and in turn the decoder will calculate the loss and backpropagate, and at this point we will just rewrite the loss as a linear combination of mean and variance. and which will backpropagate through the rest of the encoder. So now let's talk about what the paper do. So in the paper, our input would be a set of vertices, and between the vertices we will have the edge information between the vertices, as well as in this case the size information, which is the text sequence of each vertices. You can take size information at image also, but in this paper the author will focus explicitly on the text through information. Let's just say that each vertex I will have the textual information xi, which is a matrix of the size dy and li. The w here is just the size of the word embedding, and li is the length of that text sequences. Each vertex will have different text sequences length. So the main novelty of this paper, is that instead of training each vertex separately as a data instance, they try to model it as a pair of vertices. And you can see here is that in the case that there is an edge between the two vertices, they will use this kind of distribution, which is the multivariate Gaussian. And in case there is no link between the two vertices, they will use this distribution as the standard. Let's talk about this later. Okay. And in case there is no edge information between the two vertices, we just take some proportional value between the two distributions.
What about the difference between the second one and the third one?
The second one and the third one. There's a parameter here that indicate how much of a proportion we would take from each distribution.
So in the data you have an observation of no link
Yep.
pair of vertices.
You have no link. You have edge information. Also, you have note that you don't know any edge information about it. Okay, so let's talk about the second point of novelty in this paper is that they introduce some kind of mechanism called phrase-to-word alignment. So basically, this just means that before this x value here is given to the encoder, it would go through some processing step that would process it into a single vector instead, and this single vector is called phrase-to-word alignment vector. It basically means that they kind of trying to calculate some kind of similarity in the textual information between the two vertices, maybe. So basically, the input will be multiplied with their corresponding phrase-to-word alignment vectors, and they will arrive as we will arrive at the input to the encoder as this vector instead, which is just matrix multiplication between this matrix and this vector. The detail of how to calculate W's is given here, so just for you to look at it. So let's go through the overall architecture of the encoder. So in the previous step, we already have already get these two, right? And also they also use lookup table H. As far as I'm concerned from this paper, it's probably a lookup table whose parameter is trainable. But the author also mentioned in a previous section that he also deployed a version of this architecture where the lookup table H, the container base, will be produced by a paper that use the H information on it. So basically here is that the author will try to concatenate both the textual information of a node to its structural embedding. They concatenate it and they would give it to a multi-layer perceptron, which is just a neural network. And these neural networks will give back the output as a distribution. Right here you can see Mui and Mui hat. So they use Mui in case there is a edge between there's an edge between vertex I and vertex J, and they will use mu hat as in case there is no link between vertex I and vertex J. Scan two-point distribution here. So in this case, the Kullback-Leibler diversion will be calculated as the differences between these distributions versus this distribution, in the case there is a link between them. And in case there is no link between the two vertices, the Kullback-Leibler diversion will be calculated as the difference between this distribution versus this distribution here. So that's just the main differences between how they do it in this paper versus normal variational autoencoder. So the target for the decoder. So the author decided that the max pool version of the original textual embedding would be the target representation for the decoder to try to achieve. Okay. So now let's talk about some experiment. The author will try to compare to three group of paper that also produce vertices embedding. The first group is use only structural information, which is the F information between the two edges, and the second group use the both structure and size information, as is the case in this paper, but they kind of don't use variational autoencoder. And the third group is also use variational autoencoder, but they would this paper only trained so that the vertex only perform based on the task of S prediction only. Versus here, the author claimed that this discriminating method vector embedding that is produced by this discriminating method don't perform well on other tasks such as vertex classification or any other downstream tasks. So here's some data on the data set, and here's the result on edge prediction. So right here you can see this is the version of the paper that is trained to so that they only perform based on link prediction. And here's the result on the vertex classification. And here's also edge prediction based on unseen vertexes. Okay. So any other question?